Hello, my name is Matthew Nealon, and this is part 4 for homework assignment 4. And in this video, we are going to be showing how the Crank-Nicholson method of differencing works with our temperature profile, with our bar. So how that works is that let's actually start writing it out. So we start with our normal heat diffusion equation as such. So our normal heat diffusion equation is just going to be alpha times our second derivative of temperature with respect to position is equal to the derivative with respect to time, or derivative of temperature with respect to time. And then we're going to write our explicit differencing function before we find our R value, our R value that was in the previous parts. So we're going to write this out as such. It's going to be T, and it's going to be J at position J at time step n plus 1 minus T, our temperature, at position J at time step 1, or time step n, divided by our change in time. It's going to be equal to our alpha value divided by our delta x squared, and then in our parentheses is going to be our temperature with our position of J plus 1 at time step n minus 2 times our temperature at position J at time step n plus our temperature at J minus 1 or time step n. So this is where we're going to start, and this is where we are going to start for our Crank-Nicholson. And what the Crank-Nicholson actually does is that it takes the average of this side of the equation, it takes the average of this portion in the parentheses, and then it takes the average of this term in the parentheses, except we're doing an n plus 1 as well with that as well. So we're going to come over here, and then we're going to write out this very, very long Crank-Nicholson method. So we're going to come over here, and we're just going to label it as the Crank-Nicholson method. So Crank-Nicholson method. So we're going to rewrite our left side because we're going to need it at some point. And now, since we're taking the average, we're going to be having same terms up here. So we're going to have an additional delta x squared. So we're just going to write that out immediately. So it's going to be alpha 2 delta x squared. And then in this parentheses, it's going to be a very, very long formula. So it's going to be starting with what we have here. So it's going to be T J plus 1 n minus 2 Jn plus T J minus 1 n. And now what I mean by the average between this time step and a time step that's a little bit forward, or n plus 1, is that we're going to have kind of the same setup we have here. So it's going to be J plus 1 and then n plus 1. And then we're just going to rewrite this with our same J values for each step, but we're going to have that n plus 1 value there instead of just n. So we're going to have minus 2j n plus 1. And then we're going to have j minus 1 n plus 1. So this is our Crank-Nicholson's method. So now, since we're taking the average of it, what do we do from here? Well, if you can notice, is that we actually have like terms on both sides of the equation now, instead of having our normal explicit differencing method. We actually have TJ, or temperature at position J, at n+1 now, instead of just having it on this side of the equation. So what we can do now is kind of do the same method we did to find our first explicit differencing equation and how do we do that? Well, we try to find an R value, but instead of this time, we're going to call it U. So what we did for the first time, we are going to put this delta T on our right side of the equation. And we're going to call this U. That's our U value. So from here, we have like terms on both sides of the equation. So how are we going to solve this? So what we want to do now is then get like terms on like sides. So we're going to take every single n+1 value and throw it on this side of the equation. On this side, my head's blocking it. And we're going to take this value of all the values of a time step of n and throw it on this side of the equation. So they're both set equal to each other. So we're going to do that as such. So if you can tell, we have all this U value is going to be multiplied throughout this entire thing. So we have a new side on our left side, which is going to be our n+1 side. So our n+1 side is going to be negative U T J plus 1 n+1, and then it's going to be plus 1 plus 2 U T J n+1 minus U T J minus 1 n+1. That looks like an n, not an n. So that's n+1. That's going to be equal to what our normal equation would look like, at least from up here if we had that R value. So it's going to be U T J plus 1 at time step n, and then it's going to be minus or plus 1 is 2 U T J n. Then it's going to be plus U T J minus 1 n. And so with this, we can then start to find what's going. Then we can now have this entire equation out. And what we're going to do now is try to set up a weird-looking matrix in order to find how these two sides are actually equal to each other. So with this given scenario, so we're just going to rewrite the scenario right now. So we have a temperature of 50 degrees Celsius going in on this side. We have a temperature of 80 degrees Celsius coming in on this side. And the way we're going to set this up, so let's just kind of just name a lot of our, we're just going to name a lot of our positions here. But in order to set up this weird matrix, we need to adjust our matrix positions a little bit. So what we're going to do is that instead of starting our values at 1, we're going to start it at 0. And that's more to do with Python, with the way our equation and the way Python kind of sets up their own matrices as well, where we have to go from the value of 0 instead of starting at value of 1. So we're going to also do that. So we're going to do the same as well here. So J at this first position is going to be 0. It's going to go 1, 2, 3, 4, 5. And this is just an arbitrary number But from here, we then say that our temperature value is then going to be at T0, T1, and we're not going to go any farther because we need to express this at least in a different kind of way. But instead of saying, oh, this is going to be T5, this 5 is kind of just arbitrary. 5 could technically be any number. If this thing was longer, then we would have to go from this side, or we would have to express this as T infinity, or our bulk fluid, and then the position left to T infinity is going to be T infinity minus 1. And with this value, we can then start to set up our matrix. So our matrix over here, is going to be set up in a very weird way. We're going to set it up so our matrix that's getting multiplied here is actually going to be our left side of the equation where our time step is at +1. Because we want it at +1 is because we want our time steps to be at +1 is because we're starting at n minus 1. So we technically are starting at T1, starting at a temperature T1 instead of T0, because there is no value of T0 that is before T0. It would just be our temperature of whatever fluid or heat's coming in, and we don't want that. So we're going to set up an equation as such. So we're just going to take the coefficients of our, we're taking the coefficients of what we had on our left side of the equation. So it's going to be, for at least for this first one, it's going to be 1 plus 2u, and then that's the first row. And then the next row is going to be minus u, and that's going to be our second row. Actually, let me get a little bit more space, and I'll show you why in just a second. So that is our first row. And then here, since our coefficient for t, at n plus 1 is actually going to be, or at t minus 1, excuse me. Since we're kind of setting this up in a weird way, at t minus 1 is actually going to be u, or minus u, and then we're going to bring this down, so it's going to be 1 plus 2u. That looks a little funky. Let me rewrite that. And then it's going to be minus u again, and we have another row. And this value here is going to be 0. And that's why this matrix is going to be weird, because the next value below that, this is going to be 0, because there's no t of t1 value that exists for this next step. So we're just going to write it again. So it's going to be minus u, 1 plus 2u, and then it's going to be minus u over here, and we have a new row. So no minus u value is going to exist, or no value is going to exist for this point. It's just going to be 0. So technically, we can add a 0 here, we can add a 0 here, we can add a 0 here. And then we're going to add one last row to kind of show how this matrix progresses. So this matrix ends up kind of in the same way it starts. We are going to end at one point before it stops, before the actual final value. So instead of having our last value be negative u, it's actually going to be kind of the same way we started it, which is going to be our 1 plus 2u. And then the second term here is going to be u. And we're going to bring that down, because this value is going to be 0, and this value is going to be 0. All the way down. This value is going to be 0 all the way down. And then we'll end up having a negative u here and then 0 all the way down. And then this matrix multiplication is actually going to be the temperature of these various points. So this is going to be T1, T2, and I don't think I need to show any more, but where we're going to stop and where we're going to stop is going to be down here. We are going to stop at the point before our end, which is going to be Tn minus 1. Because we need to stop before it, because we don't have any more values to use at that point. So this is going to be just our multiplication sign, and then this matrix multiplication is going to be equal to our right side of the equation, which was our positive u, and then our 1 minus 2u equation. And this one is also set up a little funky as well. This one is set up a little funky as well. So we're going to set this up kind of in the same way, or in the same vein, where it's going to start with our t minus 1, and then it's going to, it's going to start with our t, this is going to start with our t plus 1, and then work its way down towards t minus 1. So from here, we have u times t times our tu plus our our 1 minus 2u t1, and then it's going to be plus plus 2u t0. Because, at least the way this thing is set up, we need that second term. Sorry, I'm going to come all the way down here. We need that second term because we are missing that, technically missing that t0 value, and we have to represent that. So, and then we're going to show the next line, or just the next line before we reach this bottom one, because that second line is going to be the pattern we follow all the way down. So it's going to be u t3 plus 1 minus 2 u t2 plus u t1. And this is our next line. And then this is going to come all the way down. So, and it's going to stop at our t minus. So coming down here, we're going to stop at 2u t minus 2, or t n minus 2. We're actually stopping 2 points away. I meant to say that. And then we're going to stop at, we'll stop at 1, blanking, 1 minus 2u, n minus 1, and then it's going to be stop at 2, which is going to be u, it's going to stop at u t n. And this is how our matrix is going to get set up, or at least is going to get multiplied when we actually put it in our code. And doing this like a normal matrix multiplication makes absolutely no sense, because you're going to have so many of these zeros in this matrix that it's just going to take forever to do it. So what we're going to do, at least in this Python code, is that we're actually going to use something called a banded matrix. This banded matrix takes basically it's asking for the diagonal at this point, and it's going to apply that to this matrix multiplication, instead of doing a normal matrix multiplication where a normal matrix assumes that there's values in the rest of these. So instead of doing that, we're going to use that banded matrix multiplication for our code. Hello, my name is Matthew Neal, and this is the code section for part 4 for homework assignment 4. In this, we're going to write code to solve the time-varying temperature profile of the bar in part 2 using the implicit Crank-Nicholson differencing that we solved previously in previous videos, And we're also going to try to vary the time step empirically to show there's no apparent stability limits on the choice of our time step, or dt. So coming from here, we have our information sheet. We're going to split this as such. We have our code here. I've already had our functions imported in. We have numpy as per usual. We have our subplots that we used back in part 2. And this time, since we were trying to solve a banded matrix instead of a normal matrix, we have something from SciPy called solve banded. So starting off, let's just do all of our givens again. So we have dx is equal to 1, dt equal to, just say 0.2. We have our initial temperature is going to be, I don't need that period there. Our initial temperature is going to be 20. Our temperature on the left is going to be 50. Temperature on the right is going to be 80 degrees Celsius. We also have an alpha value of 1. And since going down here, we have a different equation than our R value, which is going to be U. So U is going to be alpha times dt divided by 2 divided by dx to the power of 2. And this is what U is what we found for our our formula that we replaced back when we first found our Crank-Nicholson method. So that should be good. So we're going to start this off. We're going to operate this in kind of a similar way we did back in part 2, where we have a base where we start out with our length, which is going to be n is equal to 20, and then we're going to have an x, and this is going to create our x-axis lines. I lost my train of thought there. So it's going to be numpy linspace going from 0 to 1 with 20 steps in between. Now, this is where things get a little weird. Since we're solving with a banded matrix here, we have to do a couple things here. We know that that we used in our previous steps or previous videos is that we know that in a banded, the majority of the units and the numbers within a banded matrix is actually going to be 0. So what that means is that we need to very much account for that. So we're going to say A bands is equal to numpy zeros, and that's going from 3 to n minus 2. We need to have 2 parentheses because this is going to make a matrix of, this is going to make a matrix of 3 rows, and each of these matrices are going to have 18 columns to them because it's n minus 2. And then we're going to come down here and do A bands. And then what we know, at least so far, is that from our banded matrix, we know for a fact that this is going to be, sorry, I looked over there to make sure that my other recording device was on. So what we're going to do now is that our bands, we know, sorry, excuse me, I lost my train of thought. We know that starting at, when we go from the very left and to the very right, we're going to have some interesting things going on because technically our first row in our banded matrix does not have that negative u value on the left. So we very much need to account for that. So So it's going to be 1, 0, and that's going to the end. It's going to be equal to negative u. We have A bands. So this is going to be from, if I'm remembering this correctly, it's going to be that our A bands is going to be, I'm just typing this out so we can fix it in a minute. It's negative 1. Better explaining it when I have it all written out than trying to explain it while typing it out. That looks weird. So then we have negative u. So what this does is that this represents our left side over here. This represents our left side. And this is what our matrix on the left also represented. Because this is going to fill in and all the gaps that we had for our so these 4 things here are going to fill in all the gaps we need to make our banded function, or our banded matrix, excuse me. So what we're going to do now is then do what we normally did in our first one, is make our base graph. So it's going to be t, it's going to be equal to nb zeros, or np full, and then we're going to have 20 steps with each value being our t naught. So it's going to be t 0. And then our first value is going to be 50. And then our t left, excuse me. And then our final value is going to be t right. And then we're going to do figure equal to make subplots. And then do fig dot add scatter, do our x is equal to x, our y is equal to t, and then we're going to have a mode of lines, then have a name of f is 0, and just to make sure this is all working well before we get any errors, cool. This is our base. This is going to be our base, what we found earlier back in part 2 with our base graph before we start adding anything else to it. So get rid of that, and then we're going to do kind of the same thing we did back in part 2. Is that we're going to do another loop. So we're going to do fig dot, or actually not going to do fig. We're going to do for I in range of 1 to 500. We're going to make, instead of having t in there immediately, we have to deal with this banded function. So we're going to say that our right side is going to be equal to not any, we're going to make a new array with just b. So it's going to be u times t going from 2 to our final value. It's going to be plus 1 minus 2 times u times t, 1 going to negative 1. Then it's going to be plus our u times t to, it goes from our starting value to negative 2. So this is the same thing we did back in part 2, where we had it starting at our third value, and then this function, or this point, going from our second value over to right before our final value, and this one goes from our starting value to our absolute starting value to 2 points before our end. But there's 2 things that we kind of noticed in our banded function, at least for the final matrix we had, is that our first value is going to be weird, and our final value is a little wacky as well. And what that means is that we had that 2 there, so we had that 2, but that 2 is just going to be a value of this particular value plus, so it's going to be the first value this little function here is going to replace that final value, this first value, with whatever value we get up here, plus u times t, or the first value of t, and then this one's going to replace that final value of -1 plus u times t to the -1. So that's going to be our new final value. And then now we can finally start trying to solve what solve for our banded function. So it's going to be -1 equal to, and then we're going to do solve banded. And then what we do from here is that we're going to do from 1 to 1. We're going to do our first thing, the first matrix we're going to throw in there is the A bands, and then our second matrix is going to be B. Close that off, and then what we do from here is that we are going to then do the same thing we did to make our we're going to decondense our graph again. So we're going to come over here. So we're going to do if I is equal to 0. If the remainder of I divided by 25 is 0, then we're going to start printing our graphs out. So it's going to be fig add scatter it's going to be x equals x, and then it's then going to be y equal to t. Mode is going to be lines. Then our name is actually going to be the it's actually going to be our time function. It's actually going to be our I value times our time value. So what we have here is that we're going to close that off, add another apostrophe, and then that's going to make it. Then we're going to update our graphs to make it a little prettier and a little easier to read what's going on. So it's going to be fig dot update layout. Width 800, height of 600. And then our template is going to be plotly dark to make those lines pop out even more. All right, this should be fine. We'll see what we get. Awesome. Okay, this is exactly what we wanted. So we have our graph here, and it's showing how this new Crank-Nicholson method is expanding, or our new temperature profiles are being found from 50 going all the way up to our 80. And since it wants us to vary our time step to show that our stability analysis is now fine and working, we're going to come over here and say this is 1. That our time step is equal to 1, so we're going to come down here. Okay, even though our graph is a lot more tight, we actually do have, even though our graph is a lot more tight, we are able to have our stability work now, which is kind of odd, since our previous code in part 2, if we had that function higher than 0.5, the whole thing shot out into infinity. Oh, I accidentally typed something. I didn't mean to do that. Sorry about that. So we now can put any kind of time step into here, no matter what we have. So our time step is able to be any number we want. It's just going to affect how many lines or how dense this graph is going to be.